Okay, now there's some basic properties to the integrals, right? So if f and g are two integral functions in closed AB, then we have that the sum or the linear combination, the integral of the linear combination of f and g, right, is the linear combination of the integrals of f and g in that interval. Okay, and this is easy to prove. The idea is that if you go to the partitions, right, in that partition, in every partition, in every interval in the partition, the value of the rectangle, if you want, is going to be alpha f plus beta g, and you can separate that. Then the sum of that can separate the sum for f and the sum for g. Okay. Now, if f is greater, so if g is greater than f for all points in AB, then this integral will be greater. And then if f is integrable, then the absolute value of f is integrable. And this is a very interesting inequality. The absolute value of the integral is going to be smaller or equal than the absolute value, the integral of the absolute value of f. Okay? So as consequences, obviously, because if g is greater than 0, then this implies that the integral between a and b of g is going to be greater or equal than 0, obviously. And then from this we can also say that if we take m is the supremum of f in this interval, right, in AB, and then smaller m is the infimum of f in AB, right? Then if we take a function that's constant in this interval, like m only takes m and m, from this second property we get that the integral of f between a and b is smaller than or equal than m times b minus a, and this is going to be greater than the minimal value. Okay. Now we also have that this property of interval additivity. So given that a is smaller than b, that's smaller than c, function f is going to be integrable in this closed AC if and only if it is integrable in AB and BC. Okay. So that means that if it's integrable in both of them, it will be integrable in this. If it's integrable in this way, you can separate the integral. Okay, and the value of the integral will be the sum of the two integrals. Okay, now we can separate this. We can say that the value of the integral from a to b is the value of the integral from a to c minus the integral from b to c. Okay, if you think about this in terms of areas, this is kind of very intuitive, right? So and we can't how to say this, if you think about this, you can write this rule like this: ACF plus CB, right? And then you will have that the rule of additivity is maintained even if this condition is not fulfilled, right? So C is any point, right? So that is true if we say that this is true, right? The interval between B and C, how to say this? The integral between C and B is going to be equal to minus the integral between B and C. And this is important. This is a definition, okay? We have to define this integral like that because this is the integral as we have seen it so far is defined in an interval, right? Close BC, but the interval close CB doesn't exist, right? Because C is greater than B, right? So you can't use the definitions that we have seen so far about the integral, right? So we have to define whenever we have the integral of f in and the boundaries of the integral are points that are not, so this one is smaller than this, then this means that this is minus this integral. Okay,